Okay, in this example we are going to look at ball rolling down ball rolling down a track and going over a loop and going around a loop for correctness, going around a loop. So you can think of this as a sort of mock roller coaster motion. All right, mock, because mock, why? Because you don't have a ball rolling on a roller coaster. You have a cart that is going over the roller coaster in circles and highs and lows and stuff. So this is actually a classic kind of example for examining your understanding on energy and work. All right. Okay. So let's draw out a diagram for this. So what is happening? We have this track which has a loop to it, and there is a ball that starts off somewhere around here. We call this, let's say, the initial point, and then it goes around over this loop and continues in its journey. The radius of this loop that the ball needs to traverse or go around, this radius is given to us to be 21 centimeters, and which is 0.21 meters. Okay, now we want to find out how high should this ball be started from, or should this ball be released from, so that it just makes it around the loop without falling over. Alright, so what is this h for the ball to make it around the loop without falling over? Okay, so this is how roller coasters work as well. Before we get on with solving this problem, let's talk about an approach to solve this problem. Well, again, you cannot use Newton's second law of motion, because this is a curved track, and the ball is in whenever it's in contact with this curved track, the curved track will exert normal forces on it, like perpendicular to the curve at each of these points. So at each of these uh, along the track, for each of these points, the ball will feel a normal force which is always changing. The direction of the normal force is always changing. Since force is a vector, a direction change is a change in the total vector, a changing force or a changing vector. All right, let's say changing f or n, whatever. So the normal force is constantly changing, and this means that acceleration not constant, and so our kinematics breaks down. So this is another example why we cannot use Newton's second law of kinematics. We are actually being forced to use work energy theorem, but it actually makes the problem a lot simpler, as we will see. Second thing to note would be the rolling ball has a different formula for kinetic energy, and when we study rotational motion and spherical motion, we will talk about this in more detail. But for now, just for this example, know that the kinetic energy of a rolling ball is, if I can get it right, is 7 over 10 mass of the ball times the speed squared. This is the kinetic energy that we use for a rolling ball. Alright, and for this example only, we are taking a detour from 1/2 mv squared for now. Alright, so this is our kinetic energy for a rolling ball. Now let's get down to applying work energy theorem. Okay, so let's apply our work energy theorem and draw a clearer diagram to help us see what is happening in the loop. So this is the track. Let's make a loop that is more legible. Here I drew it correctly for once. So this rolling ball starts here, goes down the track, and goes this way, right? So it goes this way and then comes around and then follows this track. So what what is our target? We want to find how high this should be for the ball to make it around the loop. So we want to find h. What is h? This is what we are trying to find, and this is the path of the ball. Let's write down our work energy theorem. It is Ki plus Ui plus any work done by non-conservative forces equal to Kf plus Uf. Again, in this case, we are asked to ignore friction, so this is 0. Alright? No work is done by friction if there isn't any. So again, we have a conservation of mechanical energy, the summation of kinetic and potential. Initially is equal to the final mechanical energy. Okay, so we have to determine what is our initial point and what is our final point. Initial is here, final is here. So at this point is the final. All right. Then what else? So let's write down what we know about this. What we know about the ball rolling down. What about initial kinetic energy? It started from rest. Okay, so it started from rest means our initial speed was 0. If our initial speed was 0, then kinetic energy initial was 0. What about initial potential energy? Initially it started off from a height h above the ground. The ground is, we call y equals 0. So since it has the maximum height away from the ground, it has a maximum potential energy due to mgh, due to the height. This is equal to the final kinetic. The final is here, so it is continuing to move in the loop. So velocity final is some unknown velocity that we are not given, which is v. So it will have a kinetic energy due to that velocity, 1/2 mv squared. Well, I have done it wrong, because it is not actually 1/2 mv squared. It is a rolling ball, and we wrote down the formula for that just now, which was 7/10 mv squared. The v is at the bottom of the loop, the speed at the bottom of the loop. Then what is uf? Since the bottom of the loop corresponds to a position of y equals 0, this means that potential energy mgy is 0. Okay, therefore we have the equation mgh equal to 7/10 mv squared. Both are mass of the roller ball, and both of these terms have the same term, so we can divide it out. However, if you notice, the equation has, let's use a different color for this, and eraser. Alright, the equation has two unknowns to it. gh is equal to something times v squared, and that something is, again, let's change color. Sorry, I'm just being pedagogical about this. 7/10. Alright, so we have two unknowns, g and v, h and v, but one equation, so this would seem not to work. However, we know that the equation is correct, because work energy theorem always works. But what to do? Well, we don't have enough information for the bottom of the loop. However, let's investigate what happens at the top of the loop. At the top of the loop, let us draw ourselves a nice free body diagram. What are the forces acting on the rolling ball? The weight is there, vertically downwards, and the normal force exerted by the track, right? And let's consider plus y to go in the downward direction. Then for the ball to make it around the loop, there has to be a minimum speed at the top, because if there wasn't any minimum, if the ball goes any slower than this minimum speed, it will completely lose contact. All right, at minimum speed it is just hanging on or just touching the track. Just touching the track means this implies that the normal force is zero at that point. So we know for certainty that the normal force for that point is certainly to be zero. All right. Therefore, we can then apply F equals ma, since we know a certain constant value of F, for which we can determine a certain constant acceleration a. So in the y direction, what are the forces then? We have mg plus n, which is 0, equal to m times a. What kind of acceleration is this? It is moving in a circular loop, so the acceleration will always point towards the center of the circle. So this is centripetal acceleration. And we know that centripetal acceleration, the magnitude of centripetal acceleration, is v squared over r. So we end up with the equation mg equal mv squared over r. M's can be divided out like before, and v square is g times r. If you square root both sides, you get v equals g square root of g over g times r, which is 9.8 times, what did we have, 0.21 meters. This comes out to be, this v min, the minimum speed at the top of the loop, comes out to be 1.43 meters per second. Alright, let's see what we can do with this. Now, using this means that we just found that v min was the speed at the top of the loop, right? So, but we started off by writing our work energy theorem for the bottom of the loop. All right. So we started here and we finished here. Let's now say that the final point is changed, and the final point is actually the top of the loop. The initial is still the same at the beginning of the roll. Final point that we want to look at is that top of the loop. Let's write down our work energy theorem for the top of the loop then. So Ki plus Ui, let's just ignore non-conservative work because there isn't any. Kf plus Uf. What is Ki? The initial kinetic energy is, it started rolling, so it started from rest, meaning that initial is 0. Mgh is still mgh because our initial point hasn't changed. Now the final point has changed. It is the top of the loop. So final kinetic is 7/10 m times v squared is the v min we just found. All right. So 1.43 squared. And what is the final potential? Let's look at the slope again. So this is the ball at the top of the loop, right? And the bottom of the loop had y equals 0. So what is the height from the bottom? The radius of this circle, this is halfway, was 0.21. So this distance, this height from the bottom would just be 0.21 times 2, the diameter of the circle. So the potential energy would be m times g times the diameter, which is 0.21 times 0.21 times 2. Alright. Then we have m on each of these terms on both sides, so we can divide it out. It cancels everywhere. So simply we have the equation GH equal to 7/10, times 1.43 squared plus g times 0.21 times 2. We are solving for h, so h is equal to, divide both sides by g, 7 over 10, 1.43 squared plus g is 9.8 times 0.21 times 2. This whole thing divided by 9.8. H then comes out to be 50 or 0.57 meters or 57 centimeters. Alright, this is the height from which the ball needs to start rolling to be able to just travel around the loop without falling off. If the speed were any lower or the height was any smaller, then it wouldn't make it around the loop. The ball would fall off somewhere before the top of the loop. Alright?